All right, I think we'll get started. So welcome everybody to this Innovation Showcase Winter Series. This webinar is entitled Plant-Wide Model of Wastewater Treatment Plant, a diagnostic tool for fugitive methane emissions, and this is in collaboration with the Toronto Metropolitan University. My name is Robert Nyman, and I'm the Manager of Partnerships and Programs at the Ontario Water Consortium. The Ontario Water Consortium is Ontario's only sector support organization dedicated solely to water innovation. We bring together researchers, companies, municipalities, and governments to drive collaborative R&D, pilot testing, and real-world technology adoption. We help bridge the gap between research and market-ready innovation. And while there are many innovation organizations across Canada, none are focused specifically and exclusively on water like OWC is. OWC's collaborative model delivers measurable results. Over the past decade, we've helped mobilize over $90 million in project funding, supported or created more than 500 industry jobs, and advanced nearly 80 water technology projects. We've partnered with more than 100 academic researchers and helped build infrastructure, including wastewater test beds in London and Guelph. We do this by connecting innovators with adopters and aligning the right funding, partnerships, and support to move solutions forward. Before we begin today's session, a quick note that although this is the last webinar in our Winter Innovation Showcase series, we plan to continue our Innovation Showcase webinars in June 2026. So please watch out for announcements and registration details in the coming months. All sessions are free to join. Please also note the QR code here that you can use to subscribe to the OWC newsletter. Now I'm very pleased to introduce Dr. Elsayed Elbeshbishy, a professor of civil engineering at Toronto Metropolitan University, to begin today's webinar. Dr. Elbeshbishy will provide an overview of fugitive methane emissions from wastewater treatment plants, outlining current monitoring techniques and the principal technical and operational challenges associated with accurately quantifying these emissions. Following Dr. Elbeshbishy, we will hear from Dr. Ahmed Elsayed, Assistant Professor in Civil and Environmental Engineering at Western University, who will examine the role and potential of plant-wide models as diagnostic tools for estimating fugitive methane emissions and supporting data-driven decision-making. We will then conclude with Ismail, PhD candidate in civil engineering at Toronto Metropolitan University, who will present a full-scale Canadian case study highlighting emissions uncertainty and key sources identified through local sensitivity analysis. Elsayed, the floor is yours.
Okay, thank you so much, Robert. If you may allow me to share my screen. Okay, it is. Hopefully it is coming. I think you can see my screen now. Yes, okay.
Looks good.
So thank you so much, Robert and Rahim, and thanks so much for OWC for all their supports during the last decade for our work. We are working together for almost 10 years now. And thank you so much for everyone who's attending this session, and I hope that you are enjoying the weather in wherever the city or country you are in, because in Toronto here we have a very nice sunny weather with a little bit cold, but it's a nice weather to go outside and get some fresh air. So today we're gonna just share with you some of our challenges and the learning experience that we get through this amazing project. And today we're gonna share with you the piece of modeling part in this project. But before we start, I would like to thank very much our collaborator and supporter for this specific project. We have 16 partners from different municipalities, industries, and other research institutions as well, including OWC as one of the main supporter for this large project. So I think you are all aware of the global warming and the challenge that we have nowadays, and we cannot deny the greenhouse gas emission that is produced from the water sector in general and wastewater treatment plants specifically, which contributes to about 5% of the global greenhouse gas emission. And the main two contributors from the wastewater treatment plants are the nitrous oxide and the methane, counted for about 78% and 14% respectively of the greenhouse gas emission produced from the wastewater treatment plants. Today, we're going to focus on the fugitive methane emission, and based on our experience over the last 3 years, we can say with all evidence and confidence that fugitive methane emission in any wastewater treatment plants is everywhere. You cannot exclude a single process that is not having that methane emission except the disinfection process, but all the processes have the potential of producing a fugitive methane emission. This specific project was quite a large project focusing on the three main component that is involved in the greenhouse gas emission, starting from the sewer system, and we are having now one of its kind two pilot sewer systems, and we are in the process of producing a digital twin for the sewer system to be the first one in Canada. And we're also examining the greenhouse gas emission, both nitrous oxide and methane from the main wastewater stream, as well as the main source for the fugitive emission in the wastewater treatment plants, which is the sludge management. And there are different sources, as you may know, for the different emissions. We are focusing on methane emission in today's presentation. In this specific project, I would say the dream at the beginning, not only the goal, but was a dream to have what we call it a multi-level greenhouse gas detection, starting from ground sensors, and then we have also a handheld OGI camera, and then we go to another level with the drone and aircraft and the satellite. And at the beginning, we bought few research questions that we want to answer them. By using those different detection sensing, what is the best sensing technique for the methane emission measurements? What are the strengths and weaknesses for each of those thickness techniques? And then we want to implement the modeling side on the greenhouse gas emission measurements, both mechanistic model and machine learning model as well. So one of the goals for this project was to estimate the methane emission from the plant wide and compare it with the calculator, the default calculation using the IPCC emission factor. And then by investigating that plant-wide modeling, we want to see what are the opportunities that model can offer versus the challenges that we have when we go through that process. And this is the part that we are going to share with you our learning experience through this journey of examining the plant-wide methane emission from a specific plant site. As I mentioned, we use different sensing techniques, starting from fixed ground sensors and handheld camera and drones, aircraft, satellite images. When we went through this journey, there are a lot of challenges with each of those sensing technique, and I'm just summarizing some of the challenges that is pushed us to further invest on the modeling part, because we see that there are a great opportunity on that modeling, as Ahmed will explain in the next slides. So based on our experience with the with the sensing technologies in general, that it is a resource intensive. So it required big investment and logistically demanding, especially, for example, if you want to measure the methane emission using the drone. the logistics behind that and getting the approval and all of those things, it is really demanding and required some effort. On the other side, the accuracy and the detection limit. So, for example, the satellite imaging, it covers a big space, but it required a certain emission. Otherwise, you wouldn't be able to detect the methane emission using the satellite images and the aircraft as well. So this is one of the challenges, that some of those sensing technique cannot be applied for the wastewater treatment plants if you don't have high emission flux or concentration. And another factor that is impacting all of those sensing techniques is the weather. And if the weather is not good enough for the drone, for example, you cannot fly the drone, or if it's fog, you cannot use the aircraft. Satellite images also is impacted by the weather. And some of those techniques require the skilled operator. So not everybody or any conventional regular operator on the site can, for example, operate the handheld camera, which is very expensive camera, or fly the drone if they don't get the required license and understand how to use those. So all of those limitations give us an opportunity, like, okay, you know what? We think that there is a role for the modeling side in this project. And from that, we pushed toward this investigating the plant-wide model. And I think Ahmed will go through those opportunities and challenges for the plant-wide model. So Ahmed will share with you the role and the potential of plant-wide models on the estimation of the fugitive methane emission. So Ahmed, I'm leaving the floor to you.
Yeah, thank you. I'll share my screen now. Okay, thank you so much for having me. Thank you for OWC for hosting this great session. I want to start by thank Dr. Sayed and the whole team for involving me. I remember like I've been part of this since 2023, I think, or late 2022 as a postdoc. I have worked a lot managing the project and helping with different aspects of it. And now, thankfully, I co-supervise a couple of students continuing the collaboration when I moved to Western. So thank you to partners, to Dr. Sayed, to Amr by accepting how much annoying I am. What I'll try to do in the presentation is basically just give you an introduction. Why do we need to do this? Why we get to do this? And what was the motivation behind that? And let's start by stating the obvious. There is global warming. It's happening. Since we're doing this with OWC, so don't let any snowstorms, regardless how aggressive they are, to get you to think there is no global warming or something, or your frustration with windrows after you do all the shoveling, to get you to think like some other people who says whatever happened to global warming, it's there. I don't think we have time to go over that. Canada is actually contributing to this. I think Canada is one of the most progressive countries looking into means to mitigate it and work with it. But so far, the statistics says that we are the 11th to be contributing to greenhouse gases. If we normalize this per capita, we are kind of like the second. So we are actually contributing. And that's the reason why the government care about that, putting ambitious plans to mitigate this, aiming to get by 2050 to reach the net zero emission goal. So what does that has to do with wastewater treatment plants? There has been a lot of literature looking into the impact of wastewater treatment plants. And I would say early we were thinking maybe scope 2 emissions, that is electricity driven or related to the energy, would be the main driver. But by looking further, we can notice that scope 1 emission, the direct emission, are actually the key contributors to greenhouse gases, the direct emission that comes from different biological processes. And also in many countries, included Canada and many provinces, we rely actually on green energy sources, regardless is it nuclear, if you consider it green, or even hydro. So actually decarbonization of the energy sector is actually making direct emissions more and more important. And by looking into that, wastewater treatment sector actually considered to be the third or the fifth largest contributor to non-carbon dioxide greenhouse gases, just second to energy and agriculture. So it's important. But what really matters for this research or make this more important is actually the uncertainty or the variability around the estimation of the methane emissions, greenhouse gas in general, but for the sake of the focus of this, talk, it's the uncertainty around that. And if you look into this, and this is the research that was done in the US, looking into different treatment plants, different sizes, different configurations with anaerobic digestion, without anaerobic digestion. And what you can see here is that regardless if we're talking about the same type of treatment systems or different systems, there is variability within the treatment plant itself. You can see here from the huge variability that even estimating one treatment plant has a huge uncertainty or huge variability. And even if we look into the same type, for example, the red ones, they vary significantly into how much emission is there. So for me, this says that the key question that we have still now is how we can quantify it, or how we can manage things to do this. And actually, we have two main challenges that we have been doing progress into that. The first one is quantification methods, and I have been using this meme from the office for every single talk I give on greenhouse gases. We sometimes believe that we know exactly how to quantify it, how to measure it. But I mean, while we're making progress, I can't argue that we know 100% what we're doing. And the other challenge is basically that not every utility is equal. So, for example, in the literature, it's kind of like suggested that nitrous oxide is actually contributing to the main greenhouse gas footprint or carbon footprint coming off a treatment plant because of its high global warming potential. But our experience through our project going to different treatment plants showed that in some cases, methane can be actually the main contributor based on how treatment is managed, how the system is operated, what are the compliance limit, and how everything works. And even that profile it changes, and how dynamically is it changing is something that it changes. So my take of that is just like basically it depends. It depends on how you operate, how you manage it, and how you handle things. And that makes diagnostics and mitigation strategy a key thing, that we need to have a tool that tells us if we are now moving more and more towards a more greenhouse gas emitting situation or the other way around. So let's focus more on fugitive methane emissions and how we do this, and leading to why do we need to do plant-wide model. As Dr. Said said, for this project, we have been for, I think now 3 years or almost, I don't know, maybe 4 years, looking into different levels of or means of quantification, satellite imaging, aircraft imaging, drones, OGI cameras, ground sensors, and definitely the computer simulation. And the thing when we based on our experience, when we look into those different components, we can look into the specificity of those tools. So like how specific is it? How this tool is capable of isolating one source and saying this is the emission coming from this specific process, and also how accurate it is or how much we trust the result. So like the uncertainty around it or the standard deviation, we can look into it that way, and also how continuous it is. So like in specificity, or when we try to isolate something, we look into the special component of it, and when we look into the continuity, we look into the temporal component of it, how it's changing with different dynamics. And always when we look into those different components and try to design what kind of like campaign we will have, we will look into do main things. How much does it cost to make this feasible for treatment plants to be able to apply it? And also how good it is in diagnostics. Because if eventually we know how much we are emitting, but we don't know how we can mitigate it, how this is linking into how we operate the treatment plant, then yes, it's a valuable information, but maybe we can do better and we can do more. And I'm not going to go over every single thing. I'll just give an example with drones. This is how typically drones looks like. If we have a system like in here and we have some wind conditions, so we fly the drone, we build the curtain, and then we fly it upwind, downwind, or different means to isolate this source, and then we estimate the emissions coming out of it. And if we take this as an example, we can see that it gives us quite some good specificity. We can isolate sources. Its accuracy is okay. It's acceptable compared with other systems. It's quite accurate. It doesn't give us any continuity because we cannot keep measuring this all the time. We cannot capture any dynamics in the system. It's quite costly. You have to bring drones, which are expensive, with a pilot and have the campaign to be done and facilitate a lot of logistics. Its diagnostic tool depends on when you fly it, how you fly it, and if at that time your emissions was coming out. And I'll talk about the nature of methane emissions in a second. And if you try to make this more helpful with diagnostics, so you have to do different campaigns over 1 year or over a fixed interval of time, you will have some better continuity, but it's not going to capture all the dynamics. You will have significantly higher cost, and maybe that improve your diagnostics. But you are struggling with high cost, maybe not very good diagnostic capability, and because of the lack of continuity, and maybe accuracy is okay. And the reason why it's important, as Dr. Said was talking, That's another thing that I show always in my talks is that methane is everywhere. It's fugitive. It comes from many different reasons. If we look into this is a screenshot from a workshop in Toronto that we had in 2024. Almost every place can be emitting methane. And working with Amr, we tried to group this into some means of grouping to see which one should we care about. And actually, eventually, we ended up caring about everything. So only the one that is intentionally being produced by anaerobic digesters are the only ones that we don't need to worry about. But other than that, it can be unintentionally emitted from many different reasons of gas handling or leakage because of lack of infrastructural integrity for all the processes where anaerobic digestion can be produced. It can be because of gas liquid exchange, something coming with the sewers, so it start to be released, some unintentional dead zones in your aeration tanks. So we have emissions out of that, so it can come from everywhere. But the key here is that this is unintentional, so this doesn't have to be continuously coming out. So we won't be able to always know when exactly it's being emitted and when it's not. So it's important to have some sort of continuity and some sort of diagnostics. And if we look into any of those 5 tools, we will always struggle by balancing everything to have proper cost and good diagnostic tools. And the only thing that can give us low cost and proper diagnostic tool is basically modeling. So that's how we came up into the idea, let's use plant-wide modeling to do this, because this would be the only tool that give us proper accuracy that I would say very comparable to what we get out of the drone, and Amr will talk about how we compare what we get with what's available in the literature. It's going to be very specific. You can model any process and you can get the results. The cost is not going to be too high because it's just basically model based, and it can give you a very large diagnostic capabilities because like you can try scenarios, you can try different alternatives and test it, and you can tailor it even to be as accurate or as far from accuracy as much as you would like to. And here I just want to show that even when we fly different drones and different capabilities, and this hopefully will be published soon, we still getting a very high uncertainty limit. So even if the accuracy based on the calibrated models wasn't 100%, but it's very comparable to what we usually get out of things. So what would we do? Just very briefly, the idea is that we start to look into plant-wide models. Why not to do this? And this was part of the research that we have done, and Amr continued to look into the literature. We looked into it together, and basically we found that in many cases we just use empirical values like IPCC emission factors and pair this with activity data. If we have proper data or more detailed data, we can have a little bit more accurate estimation. But this is kind of like very static. And then we have different plant-wide models, either steady state or dynamic, but we always struggle with poor assumptions, lack of continuity if we're talking about steady state models, or that it's not comprehensive enough. It does not cover all the unintentional sources that we're talking about. It just focused on 1 or 2 assumptions. So it says AD is the key, so like it's going to be a fixed percentage out of it. So basically what we are proposing and what Amr will talk about more is basically a plant-wide model that gives us reasonable accuracy, has high specificity, cover different sources of greenhouse of methane, fugitive methane emission. It can be monitored continuously. It's very low in cost and it gives us a very high diagnostic capability. Basically, it covers all unintentional sources, so pay attention to different things that can be estimated. And also, what we have in specifically for this case, and Amr will talk more about that, is we figured out that we don't have enough data about every single case that we want to test, and we don't have enough information about the methane emission coming out of it. So we did do different scenarios to start to do some uncertainty analysis and see if those cases, given what we know from the literature, can give us or get us to end up with high methane emissions. And with that, thank you, and I leave it to Amr. I hope we didn't eat up much of your time. Thank you.
All right, share my screen, just check here. Can everyone see this? Perfect. Okay. First of all, thanks for everyone. Thanks to everyone for inviting me. I'm pretty much the youngest person here, so much appreciated. I'm a PhD candidate at Toronto Metropolitan University, and I'll cover the plant-wide model as a diagnostic tool and a quantification tool in a full-scale plant. So as Ahmed pointed out, that methane emissions can simply occur from every single process, and it's only produced intentionally in the solids train in anaerobic digesters, but unintentionally in the liquid train and also in the solids train through whether it's biogas handling, fermenters, off-gas handling, whether it's due to leaks, changes in temperature, or whatever it is. So it can be produced from it can be emitted from every single process, and that would be considered fugitive because only in anaerobic digesters where it's produced intentionally, it's considered non-fugitive. But the problem is there's a difference between the dissolved methane and the gaseous methane. So dissolved methane is coming from the sewers, from the sludge blanket of the clarifiers, from fermenters, from bioreactors, from sludge dewatering liquors that are basically recycled back to the plant's headwork. And they're only in the gaseous phase from fermenter off-gas, digester head spaces, and dewatering. And the problem is the main focus of monitoring campaigns is quantifying the gaseous emissions, and the dissolved methane remains a blind spot. And how does it remain a blind spot? It's because you need, as Dr. Elsayed and Ahmed mentioned before, that you need almost perfect conditions to take on that monitoring campaign, and plants do not operate continuously. So let's say you're doing your campaign early in the morning and the plant has already done the dewatering and has done all the recycling at night. Let's say in the different plants, depending on the sewer network, you're receiving that dissolved methane also at night or at some part of the day where you're not monitoring anymore. And all of this interferes with the accuracy of the monitoring campaign and plays also into the cost that it would be needed if you would cover the whole day, which nobody would do. So in this case, this plant that we were working with is a very large plant, and it's a biological nutrient removal plant, and so we have a lot of different process configurations that also can emit methane. It's not just aerobic, that is removing carbon or doing only nitrification. So you also have anaerobic zones, and you have anoxic zones, and you have fermenters that can also be septic sometimes, and you have recycle streams from the digesters. You have dewatering, and you also have sludge thickeners. So all the potential process units that can produce methane are existing in this plant. And the treatment here is divided into 4 trains. This is plant A. Over here, this is plant B, plant C, and plant D. And the flow rate is not distributed equally between those. And we also have a fraction of the primary sludge that is fermented in the fermenters to produce VFAs, but since it's a cold region wastewater treatment plant, sometimes the SRT is decoupled from the HRT, which means that the sludge sits in the system way longer than the liquid, which can also cause it to digest and ferment and produce methane. And eventually all of the sludge that is fermented and thickened is pumped into 8 mesophilic anaerobic digesters. And the biosolids are either treated off-site or on-site. So for us to be able to do all of this, we needed data for the model. So the plant operators were actually very kind enough to give us about 3 years of operational and performance data. So all of this data has to be aggregated into a single data set, and then has to be pre-processed. No data from a plant is going to be perfect. You'll find categorical values like some stat, NR, E, all of these symbols that don't really mean anything. They cannot be added to the model. So we're removing categorical values. We're removing any negative values because they cannot be a negative value. All the zeros, all rows where there were shutdowns, operational upsets, that cannot actually be introduced in the model. And to make sure that the data that has been removed was not enough to actually compromise the work that we did, because it was only a fraction of it, because we need actual long-term data for the model to actually be able to capture temporal and diurnal changes. Also, important part of the data reconciliation is the making sure that the data is correct. So measurement errors occur, and you can always reconcile something. So let's say the sludge COD is a bit off. You can also reconcile it with the TS data. It's more accurate and it's less prone to error, because when sludges are thickened, they tend to be very difficult to actually analyze. Missing data, such as maybe influent COD, is not measured every day, but BOD is measured every day. So we fill in the data gaps with the BOD data. So as you can see, the correlation here, we have COD to BOD is about 2.47. So we just fill in the gaps with this ratio that we've developed. Then we go to the model's setup and simplification, and we cannot just do that blindly. So we have this guideline for using activated sludge models that we always reference when it comes to these things. And there's a trade-off between model complexity and process fidelity here. So we want to simplify the model as much as possible, so it's actually easy to use and to manage, but we also want to capture everything. So we have to find that fine line between simplifying it, but not simplifying it enough that you're missing out on the benefits of the model. So we were using Sumo here. Sumo number 2 was the model that we used. It's the simplest BNR model, has 2-step nitrification and denitrification, and enhanced biological phosphorus removal, which is basically all we need. And methanogenesis is also included, so it can capture the methane from both hydrogenotrophic methanogenesis and acetoclastic methanogenesis. Similar process units like clarifiers, bioreactors, and fermenters and digesters are combined into single unit. So we have 8 digesters on site, but flow is distributed equally, and the biogas is collected from all of them at the same time. So I don't need to add 8 digesters into my model. I can just simply just put 1 digester and it would suffice. Parallel trains are also modeled as a single train. So plant A, for instance, has 4 reactors, and the flow split between them is equal. So I don't need to model the 4 trains. I can just model the whole plant as a single train. Also, physical separation units like the DAF, dissolved air flotation and gravity thickeners, are modeled as volumeless point separators, because if they're modeled as actual units, the model becomes very complex and it's almost impossible to calibrate. Also, certain operational aspects are not explicitly modeled to avoid model complexity. Something like fermenters receiving elutriation water to wash out the VFAs as much as possible. It's not modeled explicitly, but as long as we can match the characteristics of that supernatant, we're good. And then model calibration and validation. So calibration is the process of adjusting the model parameters to match the plant's behavior. And there's a steady state and a dynamic state calibration that can be carried out. And the calibration process involves basically global plant-wide changes. So influent, we had respirometry data to make sure that the influent that's coming to the plant is actually represented correctly, because otherwise anything is wrong from that point. Something like the decay rate of ordinary heterotrophic organisms. In the fermenters, we have to adjust hydrolysis rate and fermentation rates. Digesters, we also have to adjust hydrolysis rates, pH inhibition limits, and other variables like the hydrogen yield during fermentation. Sometimes these parameters are over-exaggerated and you need to calibrate them accordingly. Correction factors and effective saturation depth to make sure that the dissolved methane in the digester that is going to escape eventually is actually modeled correctly. After that, the validation ensures that the calibrated model behaves similarly with independent data. So if we did the steady state calibration on the median of the entire data set, now we're modeling the entire data set to see if it can capture the dynamics and capture them correctly also. So here you can see that the digester's flow rates from the sludges that the plant has produced are actually captured correctly. So that means the flow rate going to the digester is modeled correctly. So it gives us confidence into the with moving forward, basically. So and then we look at different scenarios. So baseline scenario, which is the existing scenario inside the plant. We have bioreactors as source of methane that can be producing anaerobic and anoxic selectors. Digesters, we have 8 anaerobic digesters, and basically any discrepancy between the reported biogas and the modeled biogas production would be considered, could be considered a leak, but not necessarily. So this is a basic source. And then you have biosolids handling. So any dissolved methane from the digesters going into the biosolids handling facility, whether it's going to be in the cake and end up whether it ends up in the cake or in the centrate, is going to be stripped into the atmosphere. And then we added potential sources for the scenario. So we have sewers, any methane stripped through aeration or turbulence. And then with the sewers, we divided them into a lower bound and an upper bound scenario. So there are networks that receive septic tank, effluents, and gray water, so they would have more dissolved methane. And then we have the typical gravity sewer network that would not have that much methane, but there is still a certain concentration of it. We have fermenters. The fermenters on site were not producing methane, but what if they were producing methane, basically? Because the off gas of the fermenter is pumped directly into the aeration tanks, so anything would be stripped into the atmosphere and would be considered fugitive. Also, clarifiers were considered as a potential source afterwards. So for the uncertainty and sensitivity analysis, we do the uncertainty analysis in Monte Carlo simulations, which is basically iterating. We have certain data as input, and each of those has a certain distribution. And we pick randomly from each parameter, and we do multiple iterations. Here we did almost 1 million iterations to be able to get a final distribution of what the output of the model would look like. And we did that to calculate the uncertainty in emissions and the corresponding emission factors. With the sensitivity analysis, we used the Sobel method, which is a global sensitivity analysis method that gives us two important metrics. One is the first order Sobel index, which provides insights into the contribution of individual variables to the output variance. And then the total Sobel index, which accounts not just only for a single parameter, but their interactions with each other. And these are the equations that we used. So total emissions include the emissions from the influent, from the centrate, from bioreactors, from fermenters, from digesters, and from the dry solids. And everything here is just calculated based on the mass of the dissolved methane that would eventually be stripped into the atmosphere. So results of the model calibration and validation from the steady state calibration, we can see steady state calibration is a lot less prone to errors compared to the dynamic state. And we can see the acceptable errors from the guidelines are very high, and the absolute error that we got from the model was very low. Also, discrepancies between whatever we were trying to predict, like sludge COD and effluent COD, 1.5% to 7.8%. All the other parameters there's very low discrepancies between them, so it gives us confidence moving forward to the validation process. The maximum error we got was 7.8%, and the acceptable error in a steady state simulation is actually 20%. For the dynamic state, this is basic. We can see the digester's influent COD load, which is going to tells us that we're actually the sludge that is going to the digester is modeled correctly. And the sludge leaving the digester is also modeled correctly. So we have confidence in the biogas that is being produced, because it's basically just a conversion factor at this point. So the error in the dynamic simulations was around 10.8%, and we didn't really remove outliers or any noise from the data after the reconciliation, so it's pretty good, especially that the acceptable error is actually 40%. So just making sure that the influent and the effluent of the digester is correct, which is our main source, ensures that the methane that we predicted is also correct. So when it comes to the primary sources, what you can see here is the discrepancies between the predicted methane and what was reported. And we can see discrepancies ranging between 0.04% to 38%. And those discrepancies do not necessarily mean that they are leaks. It could be something due to instrumentation, flow meter drift, pipeline modification, etc., or actual emissions. And this is where the diagnostic part comes in. So if you have a plant-wide model and you can see that there's a problem or an issue, doesn't necessarily have to be a leak, but at least I know where I should be looking at and how should I fix it. So I go check my flow meters, I go check my pipelines and all of these parts that can contribute to this, so I know where to go. And this is where everything is guided, and I'm not just in a mess trying to find out where the source of the emissions is, but the model is actually guiding me to where it is. Here, we're looking at the emissions from the biosolids handling. We can see that the centrate has higher emissions, but that's just basically just to the higher flow rate, because the dissolved methane in the digester is the same, and it's just split between the cake and the centrate, and you end up with a higher water content because of the dewatering. So it's not really a matter of any production here. Overall, emissions were about close to 1,100 kilograms of methane per day, but the uncertainty is almost higher than 100%, which is something that was not expected because everyone was focused on nitrous oxide most of the time because of the uncertainty of it and the huge variability. But it's the same case with methane. Emission factors here ranged between 0.005 and 0.012, and they fell within the ranges of 63 full-scale monitoring campaigns in the US, which gives us a lot of confidence in the results that we're showing. So me just sitting on my computer, just processing the data, and I was able to match the same results from those actual campaigns. When it comes to the other primary sources, like the bioreactors, emissions from the bioreactors were about 245 kilograms per day, and most of them was through hydrogen-eutrophic methanogenesis, not acetoclastic methanogenesis. So it's through the hydrogen pathway mostly, and that's because with hydrogen-eutrophic methanogens, they have a higher growth rate compared to the acetoclastic methanogens, so 1.3 versus 0.3, and they also can consume hydrogen at very low concentrations. The half saturation constant here is 0.00125, while acetoclastic methanogens can only consume, the half saturation constant is 400, which is basically the concentration at which their growth rate is halved. And so basically, when it comes to acetate, they cannot compete with other acetate utilizer, but for the hydrogen-eutrophic methanogens, they can actually do that. And also, they matched the emissions from full-scale studies. For the secondary sources, we have sewers. So sewers have never been considered in plant-wide models. They were always assumed to have stripped in the atmosphere at the headworks of the plant, but they can actually be almost as high as those from digesters, depending on the flow rate of the wastewater treatment plant. So the lower band and upper bound emissions were about 476, but the higher bound was 2,726 kilograms of methane per day. Also fermenters, because the off gas of the fermenter is pumped directly into aeration tanks. So this is the model that we did for the fermenters. And you can see the emissions here. So at 3 days and 4 days, it does pick up some methane, but then eventually just goes down. But at 5 and 6 and 7 days, even though the plant is operating at temperatures that are not ideal for fermentation, around anywhere from 9 to 18, you can still produce methane. Another source is the clarifiers, and the clarifiers are not easy to calibrate, not even for solids removal. We had to do something else here, that we had to do just some basic mass balance calculations. So the idea is that is the effluent concentration and the concentration in the sludge blanket similar or not to any soluble species? So is there ammonia being accumulating in the sludge blanket while the ammonia in the effluent is fine? And are we seeing denitrification in the sludge blanket? Are we seeing phosphorus release? And all of that. So if we are not seeing these things, we're fine. But if we are, then we calculate the release of ammonia. The increase in ammonia would give us an indication of the amount of volatile solids, suspended solids that have been fermented. And from there, we can calculate the amount of COD that has been released, and then we can see that the discrepancies in the COD can account for methane that has not been accounted, can account for methane or carbon dioxide, depending on the pathway. But this is also part of the uncertainty. So when we look at the uncertainty analysis, including sewers and fermenters increased emissions by almost 99% relative to the baseline scenario. You can see that also the emission factors are way higher than the Canadian emission factor for centralized BNR plants. So we had emission factors of about 0.034, and the Canadian emission factor for centralized BNR plants is 0.0036. So it's almost 10 times higher. Influent COD concentrations and the digester leaks have basically the most influence, but that's why it's important to include other sources that also can contribute to this, because the baseline scenario that we're looking at emissions at around 3,845, but the upper bound, we can see that's almost double. And conclusions here are plant-wide models can either minimize or remove the need for resource-intensive monitoring campaigns. They can also be used as diagnostic tools and driving decision-making and mitigation strategies. Also, fugitive emissions are significantly underestimated, and national methane inventories might need to be revised, considering emissions are only assumed to originate from anaerobic digesters. And thank you very much.
Thank you, Elsayed, Ahmed, and Amer, for your presentations. Very insightful. We now move into the Q&A section of this session. And we have a hand up right away from Andre, so I will unmute you. But for all of those that have questions, you can either raise your hand like Andre just did. You can also put it in the chat. We'll monitor that, or the Q&A section. So I'm just going to find Andre. Andre, can you raise your hand again? Seems like it's disappeared again. Oh, maybe that was a mistake. So again, if you have questions, please either place them in the chat, use the Q&A function, and or raise your hand. Or comments for any of the presenters or all of them. Just wait a minute. There's a question about share. Presumably there's a word missing. Can you please share the presentation? This session was recorded and it will be posted on our YouTube channel. And there'll also be a summary article that will summarize the entire Winter Showcase series, where all the links to the videos will be linked within and embedded in the article itself. So we'll be sharing that after. In the meanwhile, there is a question from Amanda Lake in the chat. How did you go about your calibration of the A&D model? Would ADM1 offer benefits?
I think that's a question to me. Okay, so calibration of the AD model, it's not the most complex. We basically have to make sure that the sludge that is going in is predicted correctly first. That's the first step. Second step is be able to predict the sludge that is going out. And with that, we need to adjust parameters like the hydrolysis rate. And we had to fix the beta correction factor and the saturation effective depth to make sure that the dissolved methane is modeled correctly and it matches what's in the headspace of the digester. So getting the sludge that's going in model predicted correctly, sludge going out predicted correctly, that is the first step. And then after that, we keep playing with the hydrolysis rate to make sure that everything is okay, that the steady state calibration is similar to the dynamic state validation. And the question about ADM would offer benefits. ADM is way more complex than ASM-based models and it's almost impossible to calibrate on that scale. So I would not recommend using it. Any ASM-based simulator would be a lot easier, more user-friendly for this purpose specifically.
Thank you, Amer. I'm just going to move again to Dr. Sider Rahman. Are you able to unmute yourself? You still have your hand up. Are you able to unmute yourself now to ask your question?
He asked in the chat, so it's
Oh, I see. Okay, we'll go with his question and we'll go with Angela's after. So he asks, what common models can be used to predict methane emission from wastewater treatment?
Pretty much any process simulator can do it. As long as you have an anaerobic digestion model in the stoichiometric matrix of the software, then you're good to go. We're using SOMO specifically because Dynamita is a partner on the project, but any other software that has anaerobic digestion would suffice.
Yeah, and I just want to add to Amanda's question and Dr. Rahman's question is the idea of what we are trying to propose is probably when you're trying to do this kind of simulations, gas emissions would be absent. So um, the idea is if we can simulate and represent what's happening in the liquid stream properly in terms of like carbon fate, then we make the assumption that whatever is missing can be estimated to be methane. And while that does not, it depends and varies significantly case by case, but if the assumption is like that, then what's lost in the gas phase can be estimated and be used as a diagnostic to say there is something wrong with my process over there, like what I'm represented for the biogas, and then you go see if that's a leakage or if that's some error in your gas meter or something like that. And what we have did throughout this research, and hopefully will be published soon, is that we are trying to showcase that this estimates biogas or methane, fugitive methane emission, very similar to what has been reported in the literature within the same ranges, and gives us good information about how we can diagnose and handle the treatment system. So we cannot, to answer to Amanda's comment, we cannot predict leaks, but what we can see is that we can know when something is completely offset, what we can predict with the model, and based on that we can say that this has the potential or the risk to become a leak. So that's how the assumption or the scenario looks like.
Thank you, Ahmed. And we'll move to Angela. Angela asks, what are the next steps in your research? What are the most important remaining questions for your team with appreciation? Maybe that's for Elsayed.
Okay, I'm just gonna do it quickly, Angela, and then we can have a meeting to discuss more because we have a lot to do. There are a lot of remaining questions, and this research has actually just increased our understanding that we don't know much about the greenhouse gas emissions. So there are a lot of uncertainty, as we mentioned. So there are a lot of questions needs to be answered, but specifically, for example, on the context of we're talking about modeling now, what we are using for this modeling, it's the mechanistic model, but we need to combine the machine learning modeling with the mechanistic model to come up with a hybrid model combining the machine learning and mechanistic model together. This is one of the goals that is Amr is going to work on next steps, but he's going to focus on the nitrous oxide for his next step was developing this hybrid model, for example. But there are many other questions remaining there. So cross our fingers to continue working on that and get funded by NSERC and many other interested partners. But it is unlimited question. This is what I can say. And I'm really sorry, Robert. I need to go. I have a class at 1, so I'm teaching today. So I'll leave Ahmed and Amr to answer any question. And if there is anything, just you can email me, guys. Whoever needs anything or any question can email me, and I will respond. And really appreciate the invitation, Robert and Rahim. And thank you so much for OWC.
Thank you, Elsa. Thank you for being here. We will just allow one more. If there's any final questions that Amr and Ahmed can answer for you now, we'll leave that as a final question from somebody. If not, just wait maybe 30 seconds if anybody else has any more comments or questions, and otherwise we'll wrap up. Again, you can either raise your hand and I can unmute you, or you can just put it in the chat. Although it does look like most people are dropping. Lots of thank yous. Oh, one more question snuck in. Can we use system identification?
Don't think I'm clear on that question.
Yeah, same here. I don't really understand what does he means by that.
He added to predict. I'm not sure if that's enough information. Can we use system identification to predict? But maybe he's still missing a piece of that question in order for you to answer it. So
If it's using mathematical models to predict based on data, that's basically what a data-driven model is, I think.
He did just add CH for emission.
Yeah, it's still not adding much clarity to the questions, but I'm just checking what system identification is. So it's just a methodology for building mathematical models for dynamic systems using measurement of the input and output signals. So I think that's describing a data-driven model, basically. The mechanistic model is already developed. The mathematical model has been already developed in the software. So we don't need to go that far to do it. And I didn't try because it's already available. We already know the equations. It's been available since the 1940s. They've been verified by multiple researchers in the literature, and we have numbers. And we go through the calibration and validation process to make sure that these numbers actually are correct. So there's no need for us to be doing this. We just use the package that we have, and we tailor it to our advantage to predict methane.
Appreciate it, Amr. Okay, so I think we're at the end of questions and comments. Thank you, Amr and Ahmed, for staying a little bit longer, and thank you for Elsayed, of course, and the three of you for being here, taking the time to present. We really appreciate it, and thank you for everybody who attended. Yeah, thank you very much, and have a great rest of your afternoon.
Thank you, Robert.
Okay, bye-bye.